We will now discuss a special type of relation, and the definition relies on the properties that we discussed in the previous video. So what we want to talk about is a special type of relation known as an equivalence relation. An equivalence relation is a relation that is reflexive, symmetric, and transitive. That's the whole definition. For example, suppose we have a set A containing -1, 1, 2, 3, and 4. Consider the following relation on A. Okay, so we're going to have a relation, it's a relation on A. So the relation is called R2. And as usual, it's a set of ordered pairs. And here are the ordered pairs in the relation R2. Now, just looking at these ordered pairs, it's not easy to see what this relation represents, what it means, if anything. So what we do is what's often helpful to do, you don't have to do this usually, but often it's helpful to make a diagram of the relation. So here's the diagram of the relation. And so we see we have -1, 1, 2, 3, and 4. And we have, well, first let's think about, is this an equivalence relation? So is it reflexive, first of all, right? We need it, in order to show that it's equivalence relation, we need to figure out whether it's reflexive. So reflexive means that every element of A is related to itself. Let's see, -1 is related to itself, 1 is related to itself, 2 is related to itself, 3 is related to itself, and 4 is related to itself. So those are all the elements of A. So the relation is reflexive. Is the relation symmetric? So symmetric means that if A is related to B, then B is related to A. So in other words, whenever there is an arrow going one way, there has to be an arrow going back the other way. And if we look in this diagram, that's always the case. Whenever there's an arrow going one way, there's an arrow going back the other way. How about transitive? Is this relation transitive? And it is. So for transitive, we have to check that whenever there's an arrow from A to B and from B to C, there has to be an arrow directly from A to C. Okay, and if you go around the diagram and check it all out, it works out in all cases. And even here, so you have an arrow going from 4 to 2 and from 2 to 2, from 4 to 2 and from 2 to 4, and there's also an arrow going from 4 to itself and from 2 to itself. Anyways, this is this relation is reflexive, symmetric, and transitive. Thus, it is an equivalence relation. Now, what does this relation represent, if anything? Sometimes a relation doesn't represent anything significant, but in this case, it does. So what does this relation represent? In other words, when I say that A is related to B, that one thing is related to another thing using this R2 relation, what does that tell me? Well, R2 represents has the same parity as. For example, if I say -1 R2 3, and that's true because if you look here, we have a pair -1, 3. So -1 is related to 3 using R2. What that means is that -1 has the same parity as 3. So you can see -1 is related to 1 because they have the same parity. -1 is related to 3 because they have the same parity. But -1 is not related to 2, and it's not related to 4 because they don't have the same parity. -2 is related to, 2 is related to 4 because they have the same parity. 3 is related to 1 and -1, and so on. Okay, so here, this was an example of an equivalence relation. Now, there's a closely related definition which is equivalence classes. So suppose we have an equivalence relation R on a set A. Okay, so given an equivalence relation R, and it's on a set A. And suppose we have an element of A. So little a, which is an element of big A. Again, big A is the set. Little a is an element of that set. So now we define the equivalence class containing A, which is denoted like this, with the A is in square braces. So again, the equivalence class containing A, what is it? It's the set of all elements in A that are related to little a, meaning all the elements of this big set that are related to this element. That is, the equivalence class containing A is equal to the set of all X in A such that X is related to A. Let's look at an example. So here we have the same relation as just before, right? The same relation R2, the same diagram, same exact thing. Now here, we would like to find some equivalence classes. So what is the equivalence class of -1? And of course, it's going to depend on the relation. You can't talk about equivalence classes without talking about a relation. So I couldn't just ask what is the equivalence class of -1 without using this relation first. So each, depending on what relation you're dealing with, you'll have different equivalence classes. But so for this relation, we have -1, which is an element of A, right? So that's so -1 is our little a, that's an element of the set A. And we would like to know what is the equivalence class of -1. Well, following the definition, this should be the set of all X in A such that X is related to -1. So which things in A, which of these elements are related to -1? Well, we can answer that in a few different ways. We could say, okay, which pairs have -1 in them, and then look at the other part of each pair, right? So we have, for example, we have a pair here, -1, 3. So that means that 3 is related to, I'm sorry, or, well, maybe let's look at the, well, let's look at like here, 3, -1. We have 3 is related to -1. We have 1 is related to -1. We also have -1 is related to -1. Another way to see this is to look at the diagram, right? This is much more intuitive. Which things are related to -1? In other words, which things have a connection, direct connection between -1 and those things? So we see that -1 has a connection from itself to itself. Also, there's a direct connection between -1 and 1, and also a direct connection between -1 and 3. So the equivalence class of -1, or the equivalence class containing -1, sometimes I'll say equivalence class of -1, sometimes I'll say equivalence class containing -1, it means the same thing. So the equivalence class containing -1 is equal to the set -1, 1, 3. These are all the things that are related to -1. So -1 is related to itself, 1 is related to -1, and 3 is related to -1. Now here's the thing. If I want to, let's say I want to now find the equivalence class of 1. Equivalence class of 1. So I want all things that are related to 1. Well, which things are related to 1? Well, we see -1 is, there's a direct connection between -1 and 1. There's a direct connection between 1 and itself, and there's a direct connection between 1 and 3. So in other words, the equivalence class of 1 is also this set, the same exact set as the equivalence class of -1. Furthermore, what is the equivalence class of 3, right? So let's say our little a, that's an element of A, is this element here, 3. So what is the equivalence class of 3? So it's all the things that are related to 3, all the elements of A that are related to 3. Well, -1 is related to 3. There's a direct connection between the two of them. 1 is related to 3 because there's a direct connection between them. And 3 is related to 3 because there's a direct connection between 3 and 3. So this set is also equal to the equivalence class of 3. So equivalence class of 1, equivalence class of 3, equivalence class of -1 are all, in fact, equal to each other. And they all are this set here. Now, what is the equivalence class of 2? So this is the set of all things in A that are related to 2. Well, looking at the diagram, it's easy to see that 2 is related to itself and 4 is related to 2. So this is the set 2, 4. Now, what is the equivalence class of 4? Well, it's the same as this. The set of all things that are related to 4. 2 is related to 4, and 4 is related to 4. So this is equal. Thus, R2 has two equivalence classes. So we say that this relation R2 has two equivalence classes. They are this set and this set. And this is really intuitive and obvious from the diagram, right? There are two sort of components of the diagram. There's this component and then there's this component. And within each component, every element is related to everything else. And then, there's a separation between the components. So these two components correspond to the two equivalence classes of the relation. So it's really nice, intuitive, and intuitive seeing in the diagram. Let's look at some more examples. So again, same set A. Now let's consider a different relation on A. So we'll call this R1, and this is the relation. Here's the diagram of the relation. So we see we have all the 5 elements of A, and each element is only related to itself. So -1 is related to -1, 1 is related to 1, and so on. So this is an equivalence relation because it is reflexive, symmetric, and transitive. Now, it seems obvious that it's reflexive, right? Every element is related to itself. It might not seem so obvious that the relation is symmetric. But let's explain why. So symmetric says that whenever whenever A is related to B, B has to be related to A. Well, that is true. Whenever, let's say, -1 is related to 1, 1 is also related to -1. That's true because -1 is never related to 1, right? Or for example, whenever 3 is related to 4, 4 has to be related to 3, right? If 3 is related to 4, then 4 has to be related to 3. That's true because 3 is not related to 4, so I don't have to worry about it, right? So in other words, it's like a case of where the part, the if part is false, so I don't have to worry about it. Same thing for transitive. This relation is transitive. Transitive says that whenever A is related to B and B is related to C, then A is related directly to C. Okay, that's true. If 3 would be related to 4 and 4 would be related to 2, then 3 would have to be related to 2, for example, right? But 3 is not related to 4, so I don't have to worry about it. The point is this relation is reflexive, symmetric, and transitive, so it is an equivalence relation. What does this relation represent? Well, we've seen this kind of relation before. It represents is equal to, right? So 1 is equal to 1, but 1 is not equal to 2, so we don't have an arrow from 1 to 2. 3 is related to 3, and so on. Now, let's talk about the equivalence classes for this relation. Okay, so first, what is the equivalence class containing -1? So this is the set of all things in A that are related to -1. Well, which elements of A are related to -1? Answer, only -1 itself. So the only thing that is related to -1 is -1 itself. Now, next equivalence class. What is the equivalence class of 1, right? This element of A. Well, the only thing that's related to 1 is 1 itself, so it's this set. Similarly, the equivalence class containing 2 is just the set containing 2. The equivalence class of 3 is just the set containing 3. The equivalence class of 4 is just the set containing 4. Thus, R1 has 5 equivalence classes, right? These are the 5 equivalence classes of R1. Next example. So again, we have the same set A, and now let's consider a new relation on A. We'll call this relation R3. Here are the ordered pairs, and here's a diagram. Okay, so -1 is related to itself. Then you have 1 is related to itself, 2 is related to itself, 3 is related to itself, and 4 is related to itself. And then if you look at all 4 of these, each one is related to each of the other 3, right? So 1 is related to 2 and 3 and 4. 2 is related to 1 and 3 and 4. 3 is related to 1 and 2 and 4. And then same thing for 4. 4 is related to 1 and to 2 and to 3. Okay, so this is an equivalence relation since it is reflexive, symmetric, and transitive. Now it represents, what does it represent? What idea does it represent? Well, it represents the idea of has the same sign as, right? So -1 has the same sign as -1. And then for each of these others, these are all, so this is, this is the -1, the only -1. All these are positive. So they all have the same sign as each other. So that's why they are all related to each other, right? 1 is related to 2 and 3 and 4 because they all have the same sign. They are all positive numbers. So what is the equivalence class of -1? So the only thing that's related to -1 is itself. So that's just a set containing -1. What is the equivalence class of 1? Well, what are the things in A that are related to 1? Well, 1 is related to itself, 2 is related to 1, 3 is related to 1, and 4 is related to 1. So we have this set. But this is also the equivalence class of 2, because this is the set of things that 2 is related to, that 2 is related to. And this is also the equivalence class of 3, because this is also the set of all things that 3 is related to. And this is also the equivalence class of 4, because this is also the set of all things that are related to 4. Thus, R3 has 2 equivalence classes, the set containing -1 and the set containing 1, 2, 3, 4. Another example. Same set A, and now let's consider the following new relation, which we'll call R4. Here's a diagram of it. So this is an equivalence relation, since it is reflexive, symmetric, and transitive. It represents the idea of has the same parity and sign as. So -1 has the same parity as sign as itself, but if you compare -1 with 1, they have the same parity, but not the same sign. So that's why they're not connected. Let's see. If you look at 1 here, right? So 1 has the same sign and parity as 3. It also has the same sign as 2, but not the same parity. But we're only counting things that have the same parity and the same sign as being related. So 1 is related to 3 and vice versa because they have the same parity and sign, but not 2. 2 and 4 are related, and so on. Okay, so this is relation R4. Let's consider the equivalence classes for this relation. So the equivalence class of -1 is just the set -1. The equivalence class of 1 is the set 1, 3, which is also the equivalence class of 3. The equivalence class of 2 is the set 2, 4, which is also the equivalence class of 4. Thus, this relation, R4, has 3 equivalence classes. Final example, and this is a more sophisticated one. We've seen a relation like this before. So consider the relation blank is congruent to blank mod 3, which is a relation on the set of integers. So what does this relation do? Well, it tells you whether whether integer A is congruent to integer B mod 3. So this is a relation on the set of all integers. So this relation applies to all integers, and it tells you, given 2 integers, it tells you whether the first integer is congruent to the second integer mod 3. So now, is this an equivalence relation? That's our first question. Well, we have proved in the previous video, at the end of the previous video, we have proved that if n is any natural number, doesn't matter whether it's 3 or 2 or 15, any natural number, the relation blank is congruent to blank mod n, which is the relation on Z, is reflexive, symmetric, and transitive. Right? We proved that this relation, no matter what n is, as long as n is a positive integer, the relation is reflexive, symmetric, and transitive. Thus, this relation, which is what we're actually trying to consider now, is an equivalence relation. All right, so it's an equivalence relation. So let's consider the equivalence classes. So what is the equivalence class of 0? Right, 0 is an integer. So we want to know what are all the things that are related to the integer 0 using this relation. So we're going to follow the definition, right? So equivalence class of 0 is the set of all x in Z such that x is congruent to 0 mod 3. because that's what the relation represents, that x is congruent to 0 mod 3, or whatever the zero here, 0. Okay, so how do we simplify this further? Well, using the definition of congruence, this becomes the set of all x in z, so the set of all integers, such that 3 divides x minus 0. In other words, the set of all x in z, such that 3 divides x. So in other words, we want the set of all integers that 3 divides. This is also known as the multiples of 3. And here is, well, obviously not a complete list, but this is gives an idea of what it is, right? So you have -6, it's a multiple of 3, -3, or think of it as 3 divides each of these numbers, right? 3 divides -6, 3 divides -3, 3 divides 0, 3 divides 3, 3 divides 6, and of course this list extends in each direction. Idea is it's all the multiples of 3, both positive and negative, and 0. Now here's something to notice. So this was the equivalence class of 0. What about if I ask, what is the equivalence class of 3? Well, based on what we have so far, we could already answer that, because because we know that within this category, everything has to be related to everything else, right? So within this equivalence class, every element of the equivalence class is related to every other element of the equivalence class. Well, maybe that's not so obvious, but the idea is, because of the symmetric property and the transitive property, it ends up being that all the elements of an equivalence class are related to each other, and that was true in all the earlier examples as well. But so here's the thing. So what is the equivalence class of 3? Well, we can already see that it's going to be exactly the same thing, because we see that 3 is inside here. So all the things that are related to 3 are all of these things, meaning the same things that are all related to 0. So the equivalence, so this is actually equal to the equivalence class of 3. But we can go further. What about 6? What about the equivalence class of 6? Well, the equivalence class of 6 will be all these things that are as well. So this is also the equivalence class of 6, and also the equivalence class of 9, and so on and so on. And actually, we can even go in the negative direction. This is also the equivalence class of -3, and also the equivalence class of -6, and so on. So this is the equivalence class of 0, which is also the equivalence class of 3, and 6, and 9, and so on and so on. Now, what about the equivalence class of 1? So we notice that 1 is not in here, right? So it's probably part of a different equivalence class. So let's think about what is the equivalence class of 1. So following the definition, this should be the set of all integers x, such that x is congruent to 1 mod 3, meaning this is the set of all integers x, such that 3 divides x minus 1. Well, what is this? Which numbers fall into this category? Well, it's an infinite set of numbers, but we have -5, -2, right? So for example, -2, so 3 divides -2 minus 1, right? Because that's 3 divides -3. Or let's say take 4, for example. 3 divides 4 minus 1, because 4 minus 1 is 3, and 3 divides 3, and so on. Notice it's the same, it's just like this set, but just you add 1 to every element, right? So instead of -6, you add -5. Instead of -3, you have -2. Instead of 0, you have 1. Instead of 3, you have 4. Instead of 6, you have 7. So it's the same set, just shifted over by 1 in a way. Now, we can go further and say, well, what is the equivalence class of 4? Well, since 4 is in this equivalence class, and everything in this equivalence class is related to everything else in this equivalence class, so this equivalence class itself will also be the equivalence class of 4. And it will also be the equivalence class of 7, and the equivalence class of 10. And we can also go in the negative direction, right? -2, the equivalence class of -2, the equivalence class of -5, the equivalence class of -8, and so on and so on, right? So I'm not even listing them all out, but we can see that this equivalence class is actually has many different ways of calling it. Sort of, there are many different names for this set here. You can call it the equivalence class of 1. You can call it the equivalence class of 4. You can call it the equivalence class of 7, but it's all the same, ultimately the same set. Now, notice that we have a 1 here, but we don't have a 2. So what is the equivalence class of 2? So following the same definition, this is going to be the set of every integer x such that x is congruent to 2 mod 3, which is the set of every integer x such that 3 divides x minus 2, which is this set here. So notice it's the same set as this, just shifted over by 1 to the right. And this is also the equivalence class of 5, and also the equivalence class of 8, and also the equivalence class of 11, and so on and so on. So now, something to consider, something to note here is that every integer, both positive, negative, 0, it doesn't matter, every integer falls into one of these 3 categories, into one of these 3 equivalence classes, right? So if it's a multiple of 3, it will fall into this one here. If it's a multiple of 3 plus 1, it will fall into here. Whoops, here. If it's a multiple of 3 plus 2, then it will fall into here. If the multiple of 3 plus 3, then it will fall back into here, right? Because the multiple of 3 plus 3 will come back in here, and so on. So this is so every integer, right? And also you can see here, right? So here we have 0, and then 1, and then 2, then 3, and then 4, and then 5, and then 6, and then 7, and then 8, and so on and so on. So these 3 sets will include, altogether, they'll include every integer, right? So every integer is an element of exactly one of these 3 sets. So we can be sure, we can feel confident that these 3 sets are the only equivalence relations for this particular relation, right? Because these 3, because every integer falls into one of these 3 equivalence classes. So and we also reason that all of these other things are just other names for this set. So we have 3 sets. So I would say thus the relation. Oops, sorry, there's a little mistake there. So thus the relation of congruence mod 3 has exactly 3 equivalence classes, right? This is 1, this is the second, and this is the third.